4.8, we're going to learn a method for finding zeros of functions called Newton's method. And so you've read through the book, so you have an idea of what's going on. I'm just going to look at a couple examples and kind of reiterate the concept of Newton's method. So suppose we want to find the zeros of some function, zeros of this function y equals f of x, which is to say, another way of looking at that is solving this equation f of x is equal to 0. So the way we're going to do that with Newton's method, what it's going to do is say, all right, well, I've got some function here, f of x, and it may look something like this. Okay, and let's suppose I'm interested in finding what this 0 is right here. So, and to do that, what I'm going to do is I'm going to pick some point. I'm going to call that x sub 1, and then I'm going to take from x sub 1, I'm going to go up to the function at that point. I'm going to look at the line tangent to the curve at that point. So we know how to find the line tangent to a curve at that point by taking the derivative. So here it is. Here's a line, and with a slope equal to f prime of x1. So once I know the equation of that line, then I can say, all right, well, I can find the intercept of that line. Where does the function, the line, intercept the x-axis? Well, I'm going to call that point x sub 2. All right, and once I have that point, I'm going to trace that either up or down, depending on where my function is, to my function. I'm at that point of my function. All right, now we're going to take the line tangent to the curve at that point. And again, the slope of this line will be the derivative at x sub 2. We know how to find equations of line tangents to curve. And then I'm going to say, okay, where's the intercept point there? Well, it's going to be this point right here. Let's call that x3. We're getting a little tight here, but I'll go up until I hit the curve, and then I'll find the line tangent there. You can see every time from x1, x2, x3, we're getting closer and closer to our actual 0, which, keeping consistent with the book, we'll call r for a root of our equation. And that's the basic idea behind Newton's method. Now, as they pointed out in the book, how can I find this point x2? Well, x2 is going to be the solution of the equation to this line tangent. Now, the line tangent is y minus f of x1, and that equals my slope f prime of x1 times x minus x1. And so what do we want to do then to find x sub 2? Well, x sub 2 is going to be the value of x that makes this whole thing come out to be 0. That is to say, if we solve this for y, so y is equal to f of x1 plus f prime of x1 times the quantity x minus x1. So again, this is just the equation of the line tangent. That's this line right here, this orange line is this equation right here. Solved for y right here. Well, again, this is going to be 0 at the point x2. The y value is going to be 0. So we say that 0 is going to be the function at x1 plus f prime at x1 times the quantity of x sub 2 minus x1. Again, when we put x2 in for x in our equation of our line tangent, the y value comes out to be 0. So if we solve this for x sub 2, and I'll let you guys do that on your own to verify it, we get that x sub 2 is equal to x1 minus f of x1 divided by f prime of x1. All right, and then we can continue this pattern. We could say that if we're interested in finding x sub 3, then we could do the same thing, find the equation of line tangent to the curve at x2 comma f of x sub 2, which is going to be this point right here. This is x2 comma f of x sub 2 with a line tangent with the slope of f prime of x sub 2. And we would find then that our x sub 3 point is going to be x sub 2 minus f of x sub 2 divided by f prime of x sub 2, and so on and so forth. And so we can keep doing that process, and we get a generalization. Then x sub n, our nth value, is going to be x sub n minus 1 minus f of x sub n minus 1 divided by f prime of x sub n minus 1. So all we're really going to need then is the original function and its derivative. And we need to pick a nice starting point for x sub 1. Let's look at an example here of this in action. There's a nice visual module that's given with the software that you were given with this book if you bought a new book. So here we're starting at x1 equals 1. So this is going to give us then this point right here. And if we look at our first, hang on a second. All right, let's try that again. We look at x sub 1 is equal to 1. So that's going to be the trick, is picking your first x sub 1 point. But that's equal to 1, then you can go through this process. So you can see, so our first guess was that the root is equal to 1. Now we can see that it's not equal to 1. It's closer to 0.5 or maybe less than that. But what happens? We go down until we hit the function, and then we draw the line tangent, and we go until we hit the x-axis. So the x-axis here is actually at, we hit the x-axis at 0. So you can see our x sub 2 then is going to be 0. And f of x at that point is going to be 0.1. So if we go to the next step, we go up until we hit the function, and then we draw the line tangent. Now the line tangent intersects the x-axis here at about 0.5. And according to the function here, it's exactly 0.5. All right, so now we're going to go down a little bit until we hit our function, which is just a little bit below the x-axis, negative 0.01250. And we do the next step. And let's see, we went to 0.4. So you can see we're really zeroing in on this 0. The 0 is about 0.5. The next guess was 0.44, and it's hard to see what's going on now. But as we keep going, you can see how these guesses here are getting further and further stabilized. So we could say to 5 decimal places that it's 0.44504. That's what the 0 is of this function. All right. Now, suppose we wanted to find the 0 of this function. Well, a good place to start, a good place to guess, would be maybe over here somewhere, a little bit below it. And if we take our first guess, okay, we draw the line tangent, we go up to this point. Now the next step is going to drop it down to this function and go tangent to that, and you can see we're going to be getting closer and closer to this actual root, and it looks like this root, we already have some pretty good accuracy here. It's negative 1.24698. Let's go ahead and look at another function here, and you can see what's going to happen. Let's try this one. This should find this, well, let's go over, well, let's go see what happens from here. So here we're going to probably find this 0, which is going to be at 0. Our first guess, x sub 1, is going to be 1. And the line tangent here actually takes us down to this point right here, where our x value is negative 0.85, and the function is going to be negative 0.8, so right down here. So we step down to that point. We draw the line tangent. That takes us to x of a little bit past 0, 0.2. So we started at 1, went to negative 0.8, now we're at 0.2, so we're zeroing in on this 0 here. And now we're going to go up to the function and draw the line tangent there. So we go up to the function, draw the line tangent. Now we intercept the x-axis at just a little bit left of 0, negative 0.005. And if we keep going from there, you can see that we are zeroing in on that 0 of 0. Now notice what can happen if you choose x1 poorly. Newton's method is not always guaranteed to work. Let's suppose we started with a guess of negative 3 for x sub 1. Let's see if we can get it right on negative 3 here. All right, now this would not be a very good guess, so a lot of times it's going to be very beneficial to have a graph to see where you want to guess first, because you can see it looks like our guess is going to be, our function is going to be 0. So this wouldn't be a very good first guess, but let's see what happens if we try Newton's method. All right, we go up to this, we draw a line tangent here, and we're going to go up to our curve. Well, we go up to the x-intercept of the line tangent. Now we're going to drop down to our function and draw the line tangent there, go to the x-intercept of that line. Now we're going to drop all the way down to our function. All right, that's way down here. The line tangent has an x-intercept here, so we'll drop that down to our function. Right here, line tangent, x-intercept here, and you can see what's going to happen here. We kind of get stuck in a loop. And you can see that we're actually not getting closer to the 0 at all. We're just kind of stuck over here. We're not getting closer to the 0 right here. So just be aware of that Newton's method does not always work. It's possible that you can choose a value, and sometimes you can actually choose a value pretty close to your 0, and because of the nature of the function, Newton's method will spin it out of control on off to places that won't get close to that 0. So let's go ahead and take a look at a couple examples then out of your homework section. Let's take a look at number 6 maybe first of all. We have x to the 5th plus 2 is equal to 0. With x sub 1 equaling negative 1, we want to use Newton's method to find the third approximation, x sub 3. So we want to find x sub 3 here of this equation, x to the 5th plus 2 equals 0. So what you can think about is we're finding the roots or the zeros of the function f of x equals x to the 5th plus 2. Another thing you can think of is we're finding where does x to the 5th plus 2 equal 0? Well, that's where x to the 5th is negative 2. We're finding actually the 5th root of negative 2. So Newton's method actually is another way of finding with an approximation of the 5th root of negative 2. All right, so we have this, x to the 5th plus 2 equals 0. We have our x sub 1 is negative 1. So we're going to need our f of x is x to the 5th plus 2. That tells us that f prime of x is 5x to the 4th. So now remember that x sub n is equal to x sub n minus 1, the previous guess, minus f of x sub n minus 1 over f prime of x sub n minus 1. All right, so there's our Newton's method, or you can think of it as x sub n plus 1 equals x sub n minus f of x sub n over f prime of x sub n. So x sub 2 then is going to be x sub 1 minus f of x sub 1 divided by f prime of x sub 1. So x sub 2 is going to be negative 1 minus f of negative 1 over f prime of negative 1, which is equal to negative 1 minus, let's see, if we put negative 1 in for f, we get negative 1 plus 2 is positive 1, over 5 times negative 1 to the fourth, that's just going to be 5. So we get negative 1 minus 1/5 is going to be negative 1.2. All right, so we're going to have one more step to go then. Let's go down here to do that. This is what x sub 2 is equal to, negative 1.2. Now x sub 3 is equal to x sub 2 minus f of x sub 2 over f prime of x sub 2, which is equal to negative 1.2, so we're using again negative 1.2 for x sub 2, minus f of negative 1.2 over f prime of negative 1.2. Let's go ahead and put those into the calculator. You will need a calculator on this, and I'm not sure how we're going to do this test for this in the final, but we'll let you know that as we go along here. Well, I'll tell you what, I'll just go ahead and let you put that into your calculator. We're done here at this point. I mean, you just have to go ahead and evaluate f of negative 1.2, which of course is just going to be, let's see, what's f is x to the fifth, so negative 1.2 to the fifth plus 2 divided by the derivative at negative 1.2, so that's 5 times negative 1.2 to the fourth. And whatever that comes out to be then is your x sub 3. So I'll let you guys go do that from there. And again, you will need a calculator for these problems. Nothing fancy, just a standard calculator. All right, let's go ahead and take a look at another problem like number 9. We want to approximate in number 9 the cubed root of 30. We want to use Newton's method to do it. So really what we're doing then is we're actually finding the roots of this function, x cubed minus 30. I should call that f of x equals x cubed minus 30, because if we set f of x equal to 0, we're setting x cubed minus 30 equal to 0, and so we get x cubed is 30, and so x is the cube root. Is the cube root of 30. So again, if we can approximate the cube root of 30 by finding the roots of this function f of x equals x cubed minus 30, which of course means that f prime of x is just going to be 3x squared. And so I'll let you take it from here for the most part. I mean, the biggest thing you need to do is take a good guess. And the best way to do that probably is to draw a graph. And good software, again, is this WinPlot, which is available for free on the internet. Just Google WinPlot. Should be the first one that comes up. If I do x cubed minus 30, you can see there's an intercept here. 1, 2, 3, right at 3. So, well, it's a little bit past 3, so a good guess for x sub 1 would be 3. So we'll use x sub 1 to equal 3. And so then x sub 2 is going to equal x sub 1 minus f of x sub 1 over f prime of x sub 1. So our second x sub 2 is going to be 3 minus f of 3, which is 3 cubed minus 30, divided by f prime of 3, which is 3 times 3 squared. So that's just going to be 3 minus 3 cubed is 27. 27 minus 30 is a negative 3 over 27. So that's 3 plus 1/9, looks like. 3 over 27 is 1/9, which is 3.1111, and so on. All right, and so we're getting a little bit closer. You can see that our root is going to be a little bit past 3, so that got us a little bit closer. And you're going to use that then for x sub 2. And then x sub 3 is going to be x sub 2 minus f of x sub 2 over f prime of x sub 2, which will be 3.1 repeating minus f of 3.1 repeating, which is 3.1. Or you can just use 3 1/9 cubed minus 30 over 3 times 3.1, or 3 1/9 squared, and so on. All right, and then just keep going from there. And what you're going to get eventually is you should get where your x sub, well, you can keep going, 4, 5, 6, and so on until you get 8 degrees of accuracy. You want to be correct to 8 decimal places. So what you're going to do is you're going to go until the first 8 decimal places don't change from one guess on to the next. All right, so I hope that makes sense. All right, let's maybe look at one more here, and I think then you'll be in pretty good pretty good shape. Number 15, we have e to the negative x is equal to 2 plus x. We want to find all the roots of this equation. So what we're going to do is we're going to say let f of x equal e to the negative x minus 2. I'll just put everything on one side, and so we're finding the roots of this equation. Let's go ahead and plot this and see how many it is that we're looking for. Well, here's that function, e to the negative x minus 2. It looks like there's only one root that we're trying to find. It looks like it's about negative 0.5, maybe negative 0.4 something. So what I would do here is I would try with an x1 of negative 0.5. Now I'll go ahead and tell you, well, you can see what the answer is in the back of the book on this one. You should be able to zero in on it. It's negative 0.4 something. So I'm going to try with x1 equals negative 0.5 and try and get it accurate to 8 decimal places. So again, that just means you're going to repeat Newton's method until you start zeroing in on something. Now if you keep going in Newton's method and you're not getting close to one particular number, that means you picked a bad starting point. As we saw earlier, Newton's method doesn't always work it depends on your choice of your starting point. All right, and then I want to say one more thing about one more problem. That's number 26. If you take a look at number 26, we want to find the absolute min of the function f of x equals x squared plus the sine of x. Well, mins occur. Where do those occur? They occur where the derivative is 0. So what we want to do is we want to find where f prime of x, which is equal to 2x plus cosine of x, derivative of sine is cosine, is equal to 0. So what we'll do is we're basically then use Newton's method here. And we'll just go ahead and give this f prime of x a new name. Let's just call it g. If I can call that one f. So g, we'll just let g of x be 2x plus cosine x, and then of course g prime of x is going to be 2 minus the sine of x. Now the question is, where do we start? We want to use x1 equals, and let's go ahead and plot a graph of it. X squared plus sine x. If we do that, we have, yeah, it looks like we actually have a couple of different places where this thing is going to be 0. One is going to be 0. That's true, but we should probably try to find this other one. So I would maybe start with x1 equals negative 1 and go from there and see what we can find. Wait a minute, that's not what we want to do. Actually, it looks like this is the original function f of x. I'm sorry. This is the original function, and it looks like our absolute min is going to be this point right here. This should be where our derivative is equal to 0. So let's add a new function in here. This is our function g of x, which is the derivative of f of x. We said that was 2x plus cosine of x. Yeah, sure enough, look at this function here. It is 0 right at this min. So this x value here, where our derivative is 0, that is to say where our function f of x makes a turn, is what we're looking for. We're looking for the roots of this function, 2x plus cosine x. So I would say a good place to start would be maybe negative 0.5. So I would start at negative 0.5 for x sub 1 and go from there. We want to get it to 6 decimal places. And then you should verify that whatever you get, that the point, I'll call it x, is a min. And how can you do that? Well, f double prime of x should be greater than 0. That means if you're positive, you're concave up, and your critical point is sitting at the denominator. So when you narrow this thing down to 6 decimal places, plug it into the second derivative of f, which would just be 2 minus sine x. It's the same as g prime, and hopefully that'll give you a positive value. And, well, it's going to have to, because sine can't be bigger than 1. Be a positive value, and so you'll have concave up, which means you're looking at a min. All right, should be in good shape for 4.8. Your password. The password is alembic, A-L-E-M-B-I-C, which means, well, it's an apparatus used in distillation, technically, or it can be used to indicate something that sort of happens as if in a distillation process. So, alembic, A-L-E-M-B-I-C is your password for 4.8. Good luck. Let me know if you have any questions.